For this lecture, I'm going to go over these 4 problems from past final exams and one from test 2 to review for material for test 2. The first problem here, we have triangles. In fact, let me go ahead and put the picture up here. So we have a number of equilateral triangles. We have ABC as an equilateral triangle, EED, DFG, and FHI. And also the bigger triangle here, AHJ, is equilateral. So we have these 5 equilateral triangles. And the centers of these equilateral triangles are P, Q, R, S, and T. And we also are given that the length AB is the same as the length FH here. So that means that each side of this triangle, since they're all the same, is the same length as each side of this triangle. And we're given an F. The F rotates about each of these points, P, Q, R, and S, by 2 pi over 3 in that order. And what we're trying to show is that F of B is equal to I. So when we do those rotations, B goes to I. Now let's just check here. If I rotate around P by 2 pi over 3, okay, the angles that the center of the equilateral triangle makes with each of the vertices, this is going to be 2 pi over 3, so B is going to go to C. And then we rotate around Q by 2 pi over 3, going counterclockwise. So that's going to go this way. And we're going to be someplace over here. And then we got to rotate around R by 2 pi over 3. We're getting off the picture here. And it's getting a little messy. So we want to try a different approach to explain why F of B equals I. And part of the problem with even trying this, we don't know where Q and R are. In this picture, you could move this vertex around. The size of BD and DF here are not given to us. So we can't rely entirely on this picture either. So somehow we have to be able to justify, though, that F of B is equal to I. So how are we going to do that? Well, first, there's one point that it's easy to see what happens. If we look at what happens to A under these rotations, you rotate around P by 2 pi over 3, you're going to get to B. You rotate around Q by 2 pi over 3, and you're just going to go to D. Then you rotate around R by 2 pi over 3, you're just going to F. And then when you rotate around S by 2 pi over 3, you're just going to H. So A is going to H under the map F. F of A is equal to H. So I just did each of these rotations one at a time, and A went to H. What else do we know? Well, what is F? I add these angles up. I get 2 pi over 3, 4 of them, so it's going to give me 8 pi over 3. That's not an integer multiple of 2 pi, so it's going to be rotation. And notice that 3 of these give me 2 pi, so it's rotation by 2 pi plus another 2 pi over 3. And again, when you go around a point by 2 pi, that's doing nothing. So you're really just going around some point by 2 pi over 3. So where would that point be in this picture? Somehow we want to go from A to H by rotating about some point by 2 pi over 3. So again, we know the product of these rotations is a rotation about some point by 2 pi over 3 just because of the adding up the angles and using the theorem we've been using. And we know that A goes to H just by looking at what happens to A under each of these rotations. So we want a rotation about some point by 2 pi over 3 that takes us from A to H. Well, notice that wherever that center of the rotation is, it has to be on the perpendicular bisector of AH. Because wherever that center of rotation is, say it's here, the distance from X, say, to A and from X to H has to be the same. So wherever X is, X being the center of that rotation, it's going to have to be on the perpendicular bisector of AH, again, because XA has to equal XH. And the other thing we want is for the angle AXH to be 2 pi over 3, because we're looking for a rotation by 2 pi over 3. So we're looking for something on this perpendicular bisector that has an angle of 2 pi over 3. Well, A does to T to H. That's 2 pi over 3, and T is on the perpendicular bisector. So T is the center of this big equilateral triangle, and so it's the center, being the center of an equilateral triangle, it's the intersection of perpendicular bisectors, the angle bisectors, the altitudes, everything. For an equilateral triangle, they're all the same. That's where they intersect. And so this is on the perpendicular bisector of AH, and this angle is going to be 2 pi over 3. And you can see if I rotate counterclockwise, that's going to take A to H then. So T is going to be the center of the rotation. There is another point on the perpendicular bisector that gives an angle of 2 pi over 3, and that would be on the other side of this AH here. You would have something down below here where you get a 2 pi over 3, but that angle is going to be you're not going to be able to go from A to H if you go counterclockwise around that point by 2 pi over 3. You'd have to go clockwise. So this is the right point T here. So this is a rotation around the point T by 2 pi over 3. That's what would take A to H after you do this. Again, the 2 pi over 3 is coming from the sum of the angles being 2 pi plus 2 pi over 3. So it looks like if I take B and rotate it around T by 2 pi over 3, I might really go to I here. So it looks like that's very possible, but just because it looks like it's true doesn't mean it's true. We should verify that. Because that's what we're trying to explain is why f of B is I. So we want to know why, after we do this rotation around T by 2 pi over 3, does B go to I? So what I'm going to do is to show you that two triangles are congruent here. So I've circled in this T for the center rotation in red here, but I want to look at the triangle from T to A to B, back to T here, so this triangle, and the triangle T to H to I. I want to convince you that those two are congruent. So let me color them in here so you can see them better. Those are the two triangles I'm trying to convince you are congruent. Well, let's see what we have. We have the distance from T to A and the distance from T to H are the same. T was on the perpendicular bisector of AH again, so TA and TH have to be the same length. Why are these angles the same? TAB and THI. Why would those be the same angles? Well, again, T is on the angle bisector at A, and it's also on the angle bisector at H. So JAH here, say, is 60 degrees, so this is just going to be 30 degrees. This AT is going to bisect that angle of 60 degrees. You're just going to get 30 degrees here. And the same thing happens on this side. This TH is going to bisect this angle of 60 degrees, so this is just going to be 30 degrees. So not only are they equal, they're both equal to 30 degrees. So we have a side and this angle, and we have this side and this angle. To prove these triangles are congruent, we can use side angle side. We want to say that AB is the same length as HI here. So where is that coming from? Well, that's coming from the fact that we said these two small triangles here, these equilateral triangles, have their sides of the same length. It was given that AB was equal to FH, and they're equilateral triangles, so HI will be the same length as AB. So we have these two triangles are congruent by side angle side. Now, TB is going to equal TI because we have these two triangles congruent. The other side that we haven't looked at yet have to be the same, the TB here and the TI. So TB and TI are the same length because the two triangles were congruent. And I also want to argue that the angle BTI is 2 pi over 3. Where is that coming from? We know ATH is 2 pi over 3, and if you take away this angle and add this angle, these have the same measurement because these were congruent triangles. So if you take away this angle from this ATH and then add this angle, you're just getting BTI. And so that has to be the same angle measurement because these two angles were the same. So BTI is 2 pi over 3, that angle. And that does it for us because that means that this point B, if you rotate it around t by 2 pi over 3, you're going to be on this line, but this distance and this distance were the same. That's what this said. So B is going to go to I under that rotation. So if we rotate around t, the point B, by 2 pi over 3, then we're going to be at I. And since this was the same thing as F, we see that this is just telling us that F of B is equal to I. And that's what we wanted. We wanted to explain why F of B equals I. The only thing else you could add to this is some English words. This was a final exam where they had a little bit of time on it. In fact, they had 3 hours on this final exam. So you could throw in some words to describe what's going on, but that's the argument. Let me go on to the next problem. So here, F is a rotation. I'm not telling you what the angle is or what the point is that you're rotating around, but it takes A to B. F of A equals B, where A is two particular points here. A is 0.52 and B is 0.25. Those are on the y-axis. And then we have the C on the x-axis, and F of C is equal to x0 for some number x. The problem is to figure out what x is. So I haven't told you what the rotation is. I don't know the center of the rotation, and I don't know the angle you're rotating by, but somehow we want to figure out what this x is, where F of C goes by this rotation. So let's draw in a picture and see if that will help. So I put the points A, B, and C here. A, B, C here. A was 0.52, so this is 52 on the y-axis. This is 25 on the y-axis since B was 0.25. And this is 39 on the x-axis since 39.0 was what C was. And where could E be here? I want to rotate around E to get from A to B. Again, E is going to have to be on the perpendicular bisector of AB because the distance from E to A and E to B has to be the same. So we need to put it on the perpendicular bisector, and wherever C goes to, it's going to be on the perpendicular bisector of C and that as well. But we know C is going to the x-axis here because that's the way I wrote this image here. So we're given that C maps to something on the x-axis. So if it's over here someplace, say, we're going to have to be on the perpendicular bisector of C in that point and the perpendicular bisector of AB. So let me draw that in. We have some point here, and we have something like this. And again, I'll call that the D here, that E. And E is going to have to be on the perpendicular bisector of AB and on the perpendicular bisector of CD. Again, that's just because the distance from E to each of these have to be the same if F of C is going to D. So F is a rotation around the point E by some angle that we don't know, but this is the angle. That's going to be the same then as this angle because C is also going to D and A is going to B. So we have these two angles being the same under the rotation. So what do we know? Well, this perpendicular bisector, this is an isosceles triangle, is going to divide these into two congruent triangles. These angles are going to be the same. Same thing with these angles. And since these angles were the same, each of these smaller angles are the same measurement. And we also have a right angle down here. So I'm going to use that this triangle then is similar to this triangle. The angles are the same. The smaller angles are the same. They have a right angle in common. And the angles add up to 180 degrees, so the last angle also has to be the same. Okay, so let's draw some things in here. Again, we know what these coordinates are, 25 and 52 here. So that tells me what this is. This is the midpoint. So it's the average of these 2 points, A and B. It's going to be 77 over 2 on the y-axis. So I can write that point then as 0, 77 over 2. That'll tell me the y-coordinate here. For the x coordinate, I want to take the midpoint of CD. I don't know what x is, but I can just call it x here. And C is the point 39, 0. So we're at 39 and x here. So we want to take the average of those. It's going to be 39 plus x, all divided by 2 for the x coordinate. And again, you're on the x-axis, so y is 0. So that's this point, and that tells me the x coordinate of E, because that's how far I have to go in this direction to get to E. And so I get that E is this x plus 39 over 2, comma, the 77 over 2. Now, if I'm going to show these two triangles, well, I know they're similar. If I'm going to use that, I'm going to use somehow the ratios of sides. I need to compute some side lengths here. This one's not too bad. This is 25 again. So we want 77 over 2 minus 50 over 2. That's going to be 27 over 2. Let's do the same thing down here. Use these two triangles again. So I want to know this length. Well, this is x on the x-axis. This is x plus 39 over 2. So I want to take x minus this, or 2x over 2 minus this. And that's going to give me x minus 39 over 2 for that length. So that's, again, just x minus this. So I have that length. I also know what this length is. That's the same as the x coordinate of E. So I'll go ahead and just put an arrow there. That's the length for the x coordinate of E, going from here to here. And similarly, from here to here is just the y coordinate of E. So that's 77 over 2. And now we can use similar triangles. And we get the x plus 39 over 2 divided by 27 over 2. 2 goes away in the denominator of both these, so you get x plus 39 over 27. So again, that's x plus 39 over 2 divided by 27 over 2. That's the same thing as x plus 39 divided by 27. And here we have 77 over 2 divided by x minus 39, all divided by 2. So we have 77 over 2 divided by x minus 39 over 2, and the over 2's are going to cancel. You just have 77 divided by x minus 39. So we cross multiply here. We have x squared minus 39 squared is 27 times 77. This is the 39 squared plus 27 times 77. You add these together, you just get 3,600. So that's x squared, so x has to be the square root of that, or 60, or minus 60. So x is plus or minus 60. The problem said there were two answers. We got 2. Sort of see, well, this makes sense. This might be 60. It's possible. Where would the minus 60 be coming from? That would be way over on the other side someplace. Well, the idea is if I take a point about here, then if I look at a rotation around this point by, well, we don't know the angle. What would the rotation be by? So if I go from A to here, it's going counterclockwise, so it's a big rotation. It's going around this way, around this point, to get from A to B. If I do the same thing now with C here and go counterclockwise, the same angle, it's going to be over there someplace. And that's where the minus 60 is coming from. But the two values for x here are plus or minus 60. And that finishes this problem. Let's do this question. So here we have a triangle, and maybe it's best to go ahead and just show you the picture. So we have this triangle ABC here. I think the B and C are there, ABC. And we're drawing squares off the sides AB and AC here. X is the center of the one squared off side AB, and Y is the center of the square off side AC. And M is the midpoint of BC. And we're told that F is a rotation about x by pi halves, followed by a rotation about y by pi halves, followed by a rotation about m by pi. Okay, so we're doing all those rotations. And what are we trying to prove? Let's see. First, we want to explain why F is the identity translation. So what is the identity translation? F is mapping some points to points, and if we're translating that means we're moving them all the same amount in the same direction. So if we have a little a and little b, say, for the point defining the translation, we want to move x to x plus little a and y to y plus little b, and that tells you what's happening to a point xy. You're adding the same amount to x and the same amount to y for every xy in the plane. Okay, so what does this mean? The identity translation would mean that the amount we're adding is 0 to both x and y. That points aren't really moving. So if I take f of xy, I get xy back. So that's what we're trying to prove. Well, first let's see why it's a translation. We add the angles together, pi halves, and pi. That adds up to 2 pi. 2 pi is an integer multiple of 2 pi. It's 2 pi times 1. So our theorem tells us that this is, in fact, a translation. So we know it's a translation. Okay, now how do we decide how much we're translating by? Why it's the identity translation? Okay, so let's see if you can tell me a point that I can go through the rotations for and tell what happens to it. So we want a rotation first about x by pi halves, and then a rotation about y by pi halves, followed by a rotation about m by pi. And we want to look for a point that we can say, hey, yes, I know what happens to it by doing those. After rotating about x by pi halves, then y by pi halves, and then by m by pi, I see what happens to it. Do you see a point like that? You do? Okay, good. So yes, you want to look at B. When you rotate B around x by pi halves, you're going to go to A. And you rotate A around y by pi halves, you're going to be at C. And then when you rotate around m by pi, you're going to be back at B. So B is going to A, is going to C, is going back to B. So that's what F is doing. It's rotating about x by pi halves and y by pi halves, and then m by pi. So F takes B to B. Well, that means there's one point that's not moving under this translation we had, and that point is B. B is going to A, to C, and then to B, so it's F of B is B. So this translation, whatever it is taking B to itself, and so the little a and little b we're talking about that we're adding to every x and y, those must be 0 because whatever b is, it's not moving. We're not adding anything to those x and y's. So f of b equals b means you have the identity translation then. Sometimes it means it's a center of rotation, but we know f is a translation because we added the angles. So in this case, it means it's the identity translation. You're not moving points. Okay, so this is just taking everything to itself. And now it says to use part A, down here for B, and explain why the triangle XMY is an isosceles right triangle. Isosceles means we want two sides to be the same, and we want it to be a right triangle. So it looks like the angle at M is going to be 90 degrees, and these two sides then will be the same length. This will be the hypotenuse. So how do we prove that? Well, we want to somehow use this F. We want to use part A. We know F is identity translation. We want to use that somehow. And it's nice to find another point that we can sort of examine using these rotations. Not quite as easy as B, but there is something we should kind of look at, and that is what happens to X, because at least with that first rotation, I know what happens. If I rotate about X and take the point X, it doesn't move. That's the center of rotation. So when I apply the rotation around X by pi halves to X, X stays where it's at. So X doesn't move under that rotation. what happens with y. We want to rotate x around y by pi halves. I'll make room here. Let's say that goes to x prime. So I've rotated x around y by pi halves. And now what I know is after I do the next rotation, I have to be back at x because f takes every point to itself. So f of x has to equal x. And first of x started here, didn't do anything, and then it went over here. And the last rotation I need to do has to take x prime back to x. So we want to rotate around m by pi for this last rotation. So that tells us that the mx prime has to be mx. And the other thing we get is that these are all in a straight line because we're rotating by pi. So again, x prime has to go to x by rotation about m by pi because f was the identity. So f has to take x to x. So we get that then that again, the mx here and the mx prime are the same length, and these points x, m, and x prime are all in the same line because it was rotation by pi. So let's look at this triangle. This was a triangle we were interested in. We were trying to prove that this triangle is isosceles right triangle. Well, notice that this triangle and this triangle are actually congruent. So this side and this side are the same. This side and this side are the same because x, yx, and yx prime are the same because we got from x to x prime by doing a rotation around y. And this side's equal to itself. So that means that these two triangles are congruent by side, side, side. This side's the same as this side, and this side's the same as this side. And that makes these two angles the same then. And because this is 180 degrees, each of them is going to be 90 degrees. So this is a right angle. This is 45 degrees because this and this are the same length, and this was 90 degrees. So this big triangle, xyx prime, is an isosceles right triangle. And so these two have to be 45 degrees. So we have 45 degrees and 90 here. That makes this 45 degrees. So we have an isosceles right triangle like we wanted to show in this picture. So that finishes this problem. It shows that this XMY triangle is in fact an isosceles right triangle. So the last problem I want to do for this lecture is the following. It's from an old test 2. I have two angles alpha and beta, and I'm given that alpha plus beta equals pi. Something like this works when it's not pi, but pi makes this a little bit easier. And I have 2 points A and B, and I want to rotate around A by alpha and then B by beta. Since the sum of the angles is pi, and that's not a multiple of 2 pi, that means that this should be a rotation around some point C by pi. And what you're trying to justify is that C is actually on the circle with AB as a diameter. So A and B are the endpoints of a diameter. The midpoint of those is A plus B over 2. That'll be the center of the circle. So let me go ahead and draw a picture here. We have A and B that we're rotating around. And I want to use that diameter AB, get the midpoint, A plus B over 2. And we're saying C should be someplace on this circle going through A and B and what's centered there. So that's what we want to justify. That somehow C is on this circle. And the idea is to try to find exactly where C is in this picture. How? Well, it's a good question. Somehow we want to rotate around A by alpha and then B by beta. Well, what to think about is the fact that if I divide both sides of these by 2, I get alpha over 2 plus beta over 2 is pi over 2. So it might take a little while to think of the right solution here, but the idea is to look at alpha over 2 and beta over 2 in this picture down here by drawing an angle, say from B to A over here, where the angle is alpha over 2. So let me draw that in. So I'm just drawing in, making an angle here of alpha over 2, and I put where I hit the circle here. Now I'm going to do the same thing on this side. Okay, so this is alpha over 2 and this is alpha over 2, these angles. And then notice if I go ahead and draw in this angle here, so that make triangles out of these, that you're going to get a right angle here and here because this is a circle and this is a diameter. And so as we discussed before, when you go from A to a point on the circle to B, you get a 90-degree angle. So you'll get a 90-degree angle there and you'll get a 90-degree angle there. And since that's pi halves, they have to add up to pi. And you have alpha over 2 here. You have pi over 2 here. When I take the pi over 2 minus alpha over 2, I'm going to get beta over 2. So these two have to add up to pi over 2 because this was pi over 2, and they have to add up to pi. So again, this is just coming from the fact that these three have to add up to pi. We get alpha over 2 and beta over 2 is pi halves from here, and the other pi over 2, a right angle from here because this is on the circle. So this is what the picture looks like. Now it's not too hard to see where C is. What happens if I take this point and rotate it by alpha around A? We're going to go over here. Right? This be alpha, this combined angle here. These lengths will be the same. This is just a mirror image of this side. So this length is going to be the same as this length. And we're going to go from here to here then if I rotate around A by alpha. But now if I rotate around B by beta, going counterclockwise, this point's going to go to here. This angle will be beta, the sum of these two, and this length will be this length. So this is just going to go back to here. So if I start here and I do this first rotation and then do this other rotation, I'm going to end up here. This goes to here and then back under these two rotations. So this point isn't moving. And again, we know this is a rotation around some point by pi. And the only point that doesn't move when we do these two rotations is the point C itself, the center of the rotation. So this has to be C. So C is right there in the circle. And all we're trying to do is show it's on the circle. Not only did we show it was on the circle, we found where it was on the circle. You've taken alpha over 2 here, beta over 2 here. This is a right angle, and it's just going to be this point right here on the circle. So that's where C is, and that finishes this problem. And that finishes this lecture as well.